going to start working our way through the various structures included within the nervous system. We're going to start with the spinal cord, which is one of the two components that make up the central nervous system along with the brain. The spinal cord is located in the dorsal side of the body, which makes sense because dorsal means toward the vertebral column, and our spinal cord is contained within our spinal canal, which is made by the vertebral column. It's going to run from the superior end of the body to the inferior, from the head down towards the opposite end. It's found in the vertebral canal, as we said. One thing to note, and we'll talk about in a little bit, is that the spinal cord is not consistent in diameter, right? You can see that there's a cervical enlargement, there's a, lumbar enlargement as well. And we'll talk about why they exist in a little bit. Well, what is the function of the spinal cord? Very simply, it's a relay station. It's to relay information from the periphery to the brain and the brain to periphery. So it's a way to get our sensory input up into and through the central nervous system, and information from the central nervous system back out to our various effector organs. Now, it makes sense that the delicate structures of the central nervous system, the brain and the spinal cord, we want to make sure that we protect them. There are very elaborate means by which we use to protect these structures. I'm going to talk about them right now with respect to the spinal cord, but keep in mind that basically they are the same protection when we get to the brain. And when we get to the brain, I'm just going to go, okay, remember we got this, and off we go, because we're going to discuss them in detail in the spinal cord. But they're not separate structures, they're continuous. We're going to divide them up because we're talking about the spinal cord separate from the brain. The bone of the vertebra, and obviously we're not going to have vertebra for the brain, but there will be bone involved. So, first thing we're going to encounter is the bone, and that's probably one of the most sturdy ways that we protect this delicate tissue. Then we have the meninges. Meninges, it's a fancy word, right? Meninges is simply these various layers of connective tissue that wrap around both the brain and the spinal cord and help give them structure, help protect them from damage, help protect them from the outside world, if you will. But what we have to talk about first is the epidural space. Epi means what? Above, upon, around. So the epidural space is going to be above, upon, around the dura. Okay, this is going to be the space between the bone of the vertebra and the outermost of the meninges, which will be called the dura mater, which we'll talk about in a moment, but that's where we get the dura from. So this epidural space is the space between the bone of the vertebra and the outermost meninges. This is typically filled with a cushion of fat and connective tissue, and that makes sense because as protective as the bone is, you don't want the delicate structure of your spinal cord slamming around in that hole, banging against the bone. So we want to kind of surround it so it's kind of packed in there. And if we look, we have a bone of a cervical vertebra, right? The yellow, just deep to the bone, that's that adipose tissue or the fat that we're talking about. And again, when I look at adipose tissue, as I've told you many times, it looks to me to be bubble wrap. And this is another instance where that analogy really kind of works because it's in there to act kind of like bubble wrap, to keep things from slamming around in that space. Now, 3 layers of meninges. Right, we're going to work, again, we've been working from the most superficial, the outermost, the bone, and we came into the epidural space, and now we're going to come in again and hit the outermost of our meninges. Now let's talk about this diagram for a second. Every author uses something very similar to it, and it can be confusing for students. You'll see it looks like there's 3 bands. Those are the 3 maters, the 3 meninges. If we start at the bottom, it's very thick and dense looking. That's the outermost. Deep to that, we go up a step. Deep to that, we go up a step. All three of these layers are continuous all around the spinal cord, but we've cut them away so we can see what's deep to, what's inside of that particular layer. So we're going to start with the dura mater, the outermost layer, and in this diagram, it's going to be the bottommost band that you see. It's tough, dense, irregular connective tissue. As we say, it's the outermost layer. Dura. What does dura make you think of? Me, it makes me think of durable, and durable is something that's tough and has body to it, and that's where the name came from. And you'll remember when we talked about regular connective tissue, all of the fibers go in one direction. It's really, really strong in that one direction. However, it's weak in any other. Irregular dense connective tissue is the fibers are going in all different directions. That makes that tissue even stronger. So that's why it's a good thing to have this dura mater made up of this irregular dense connective tissue. Deep to that is the arachnoid layer. Arachnoid comes from what you think it's going to come from, arachnid, right? This is sometimes referred to as the spider layer. There's a couple of reasons why. We'll talk about the first here. We'll talk about the second when we talk about the arachnoid layer in the brain. I have another diagram specifically to the brain, and it kind of shows you another reason it's referred to as the spider layer. But one reason is that it's a very delicate layer, and it's web-like, like spider web-like. And it kind of looks that way, right? If we look at that diagram, it's the middle band. It looks kind of sheer when we look at it. Deep to the arachnoid layer is the pia mater. This is a transparent layer of collagen and elastin fibers. What do you think the job of an elastin fiber is? Or what would be a characteristic of an elastin fiber? Well, when I look at that word, when I hear that word, it reminds me of elastic. And elastic is stretchy. And when you think about all that your spinal cord is going to do, it's contained within your vertebral column, and you can bend and twist that vertebral column in many, many, many different directions. You want there to be a covering that's going to bend and stretch with that, but go back to its original shape and help protect that spinal cord. So that's really, really helpful. We also have to address the subarachnoid space. The subarachnoid space is just what it sounds like. It's the space below, deep to the arachnoid layer. So it's going to be a gap, a space between the pia, the innermost layer, and the arachnoid layer, the next layer. This space allows cerebrospinal fluid to flow around the spinal cord and the brain when we get there. It's very, very important that we have this ability to have circulation, if you will, because we have to be bringing fresh cerebrospinal fluid in with oxygen and ions and glucose and all kinds of nutrients, and we have to get rid of the quote-unquote used, right? So we have to have a way to move it through. Well, there's not a teeny tiny heart in there, so we have to have another means to move things through, and we have to have a space to move this fluid through, and that's the subarachnoid space. We use this fluid, the cerebrospinal fluid, diagnostically. We get at this cerebrospinal fluid by doing a spinal tap. It's actually now more commonly referred to as a lumbar puncture. This is accomplished by taking a needle, putting it between vertebrae that are stacked one on top of another, and aiming that very long needle into that space. That's the subarachnoid space, and that's where the cerebrospinal fluid flows. So that's the target for a lumbar puncture or a spinal tap. It's used to diagnose spinal meningitis. Most of us, thank God, have not had to have this occur to us. From what I've been told, it can be quite painful. The spinal cord is about 42 to 45 centimeters long. It extends from the foramen magnum of the occipital bone, so it's going to go from the bottom, if you will, of the skull, down to about the second lumbar vertebra. Okay, so it doesn't go all the way down to the sacrum, it doesn't go all the way down to your butt, it ends in the lumbar region. And that ending is called the conus medullaris. It's referred to as the tapering end of the spinal cord. If we look at our diagram, conus is going to tell us it's cone shaped, so it kind of looks like the end of an ice cream cone, right? And medullaris, middle, and it's right smack dab in the middle of your body. Okay, it's going right down through your spinal canal, formed by your vertebral column. We then have the cauda equina. These are nerves that are going to branch from the spinal cord. Now, if we break this name apart, cauda, the root caud refers to the tail, and equina is equine. Does anybody know what an equine is? That's a fancy biological name for a horse. So we're saying that these nerves branching from the conus medullaris look like the tail of a horse. And in fact, those farmers among us will look and say, yeah, it does kind of look just like the tail of a horse. And that's why it's referred to as the cauda equina. These nerves will branch out and service the inferior end of your body, your legs, your pelvic cavity, those sorts of things. Back to our spinal enlargements that we mentioned. Again, the top bulge, for lack of a better word, top bulge of the spinal cord, that's going to be our cervical enlargement. This is where we're going to have a large number of nerves leaving from the central nervous system going to your upper extremities or your arms. Well, if I'm going to have an enlargement for my upper extremities, my arms, I'm going to have an enlargement for my legs, and that's the lumbar enlargement. And again, they're larger in diameter because there's a higher concentration of neuron cell bodies, and they're bigger and they're going to take up more space, and there's more of them in that area, so there's going to be that kind of bulge that we see. Now, when we look at your spinal cord in cross-section, and this will be helpful for your lab content, you'll notice that it's divided into halves, a right and left halves by grooves. Let me get this all up for us, okay? We have the anterior median fission, which is going to be on the anterior or ventral side, and we have the posterior median sulcus, which is going to be on the posterior or dorsal side. And you'll see that those two indentations divide quite nicely our spinal cord into a left side and a right side. When we talk about gray matter with reference to our spinal cord, we're going to identify it as H-shaped. To me, in most of the diagrams that we use, to me it looks like the top of a bikini, right? At the center is the central canal, and that is a space, a hole, an opening that will allow for the circulation of cerebrospinal fluid. It's going to run the length of the cord, so this is going to allow cerebrospinal fluid to flow down through the middle of our spinal cord, as our subarachnoid space allows cerebrospinal fluid to circulate around the outside of our spinal cord. Gray matter consists mainly of association and motor neurons, and because it's gray, it is going to be made up mainly of cell bodies, which makes sense, and unmyelinated nerve fibers. It acts as a relay station between the peripheral nervous system and the brain, so information coming into and out of the brain from our sense organs, our sensory receptors, will pass through